screen sharing. Okay, so I will start by sketching out a simple model, game theoretic model of strategic voting, right? What we saw so far is a model of statistical voting, where each voter was assumed to vote for the correct option out of two, with some exogenously given probability. So we didn't model what the voter's information is, what the voter's objective is, or what the decision-making context is, right? What is the size of the jury? What is the voting rule? Is it simple majority? Is it some sort of unanimity requirement? All of that was glossed over, yes. And there was this just assumed exogenous probability. And then the law of large numbers sort of kicks in quite easily and carries the day. And so we end up getting Condorcet kind of results in most situations. One issue which I don't know if I remember to discuss towards the end, I always run out of time towards the end, so sometimes one or two points get lost. One critical assumption in the previous discussion on statistical jury theorems, we assume that the probability of voting for the correct option is statistically independent across voters. Yes. Now, what if they're not? What if they're correlated to some degree? That if I have voted for the wrong thing, it maybe increases your probability of also voting for the wrong thing. Maybe because we read the same newspapers or listen to the same opinion leaders or some sort of correlation device like that. So, the statistical jury theorem literature sort of generalizes the kind of result that I discussed by allowing, for example, for some amount of correlation. If the correlation between the votes is 1, then of course there's no hope of getting Condorcet kind of results. That whenever you make a mistake as a voter, I also make a mistake with probability 1, then we are essentially casting one vote, right? And so there's no hope for any kind of information aggregation or wisdom of crowds. So you need a correlation which is less than 1 or sufficiently less than 1. We assumed a 0 correlation by statistical independence. You don't have to literally assume 0 correlation, but some of these papers, like the paper by Krishna Ladha and others, they basically try to find an upper bound on how correlated the votes can be, and they calculate some sort of upper bound. So that generalizes that class of models. Okay, but moving ahead, I want to get to the strategic voting models. I don't remember if I even started on this. Did I start on this model? Anybody? Okay. All right. So this is going to be an explicitly game theoretic model, right? So there's a number of voters. Now, voters have objectives. We won't assume them to be automatons or machines, right? They're purposive, conscious decision makers. So each voter's payoff depends on two things. One is the state of the world, and the other is the decision that the jury collectively takes. Okay? So these are state-dependent preferences, as usual, as almost throughout this course, starting from Crawford-Sobel. Now, we'll again take a very, very simple structure. All of these can be, many of these aspects can be generalized. So the state of the world can take two values, I or C, which stands for innocent or guilty, sorry, I or G, which stands for innocent and guilty, right? So the defendant may be innocent, the defendant may be guilty. And the decision could be either convict or acquit with capital letters. Yes. So the way we'll write down preferences is that if the correct state-dependent decision is made, meaning a convicted, an innocent defendant is convicted or a guilty defendant is acquitted, in both the cases, the payoff is zero. That's normalization, right? The other payoff numbers will be negative. So the zero is the best possible payoff, right? As you know by now, as advanced students of economics, what matters is the ordinal payoffs, not the cardinal payoffs. So zero doesn't mean something bad. It actually means in relative terms, it's a good thing. Now, if the wrong decision is made, so to speak, for example, if an innocent person is convicted or a guilty person is acquitted, then there's a cost, there's a utility loss reflected in these two negative numbers. Now, there's no reason to assume that the cost is the same for both kinds of errors, right? For example, you may care much more about sending an innocent person to prison than letting a guilty person go free, right? You may think that the first kind of mistake is a more morally serious mistake, right? It's really abhorrent to think of innocent people behind bars. And you know, the rhetoric in law and so on sort of plays up that that is a more serious mistake, right? So the way we can express payoff and preferences about avoiding the two kinds of mistakes, the relative cost of avoiding the two kinds of mistakes, is in this manner, right? So Q is the relative importance of sending an innocent person to prison, and 1 minus Q is the relative cost of acquitting the guilty. Yes. So obviously, if Q is higher, that means we are more concerned about the first kind of error compared to the second one, right? And we'll take Q to be somewhere between 0 and 1. Now, it's very easy to see that Q effectively then becomes the threshold of doubt, meaning that after processing all the information, if a juror feels that there's a Q or higher probability that this person is guilty, only then will the juror want to convict the defendant, right? So Q will turn out to be the minimum posterior belief necessary on guilt for conviction to be the optimal choice for these jurors, okay? That is very easy to show, and I'm not going to, show it here. You can calculate. Q will basically, it will affect the calculation of posterior payoffs from the two decisions, and the higher is Q, the more attractive is the decision to convict. Now, and we'll also take the prior on guilt to be pi, right? So before any information comes in, anybody receives a signal of any sort, everybody believes that with probability pi, the defendant is guilty. Now, one thing to note is that, I have not put down any I subscripts, right? I haven't said that, juror I has a cost QI if an innocent person is convicted, right? So there are no I subscripts in the utility function, and there's no I subscript on pi. So that means that it's a common interest voting game, right? Everybody's preference is fundamentally the same, and everybody starts with the same common belief, namely pi, right? Their beliefs diverge along the way because they receive private signals, which I haven't talked about yet, but I will talk about in the next slide. But before receiving the private signals, they have the same belief on guilt. Now, let me very quickly mention a couple of things. Q is the threshold of doubt, Yes. In the language of law, they often say that a defendant can only be convicted if guilt is beyond reasonable doubt, right? So what does reasonable doubt mean? Is it a 10% chance that this person may not have committed the crime? Is it a 1% chance? How much is it? Yes? Anybody? The law doesn't quantify it, right? The law just has this vague language that guilt has to be established beyond reasonable doubt. In terms of a model, Q is the reasonable doubt threshold, as I said. In practice, what people think Q ought to be is debatable. Some people, some legal philosophers may even say that we can't quantify Q. Yes. But we are economists, we have to quantify things because we do quantitative analysis. So we cannot but sort of build up a theory where Q is well specified. It could be 1%, it could be 1 in 1,000, I don't know. Something is there. Another legal rhetoric, which might clash with the way we are modeling this, is regarding pi, right? In law, they often say that a defendant is assumed to be innocent until proven guilty. Now, that might suggest, if you take it at face value, that the prior on guilt ought to be 0, that pi equal to 0. Yes. But mathematically, statistically, by the logic of probability, we can't take pi equal to 0 because then Bayesian updating will give you a posterior of 0, no matter how strong a signal there is. The posterior belief will have to be 0. If you're certain at the beginning that this person is innocent, we can never have any doubt creeping into our minds about guilt. Yes. So again, we cannot quite literally adhere to this nice sounding statement that a person has to be innocent until proven guilty. Maybe that rhetoric suggests that pi should be taken to be low, right? Not high, but how much low, I don't know. Anyway, we'll keep these things general. We'll assume that there are numbers out there in everybody's minds and in their preferences, which capture the notion of reasonable doubt thresholds and how much innocence is to be assumed in the beginning. Okay, now, here comes the important informational assumption. Voters receive private information. And we're going to assume that private information is basically a signal. Each voter receives her own private information, right? So whatever was on the previous slide is common knowledge. Every voter knows all of these things, these numbers that we have put down. And more than that, every voter knows that other voters know this. And so everything is common knowledge. Now, every voter also knows that there's this information structure. But the signal realization of voter J is observable only to voter J and not to other voters, right? So voter J gets a signal Tj, which can take one of two values, small g and small I. Capital G and I describe the state of the world. Small g and I describe the outcome of the signal, okay? And there's a conditional probability distribution like this. So if the true state is capital G, the defendant is actually guilty, PG is the probability that any particular voter will see a guilty signal, right? But there is some probability, 1 minus PG, that even when the defendant is guilty, some voter will observe an innocent signal. And likewise, when the true state is innocence, there is this marginal probability distribution. Very generally speaking, this signal structure suggests that there is some information content in the signals as long as these probability rows are different from each other, meaning the numbers are not the same, as long as PG is different from 1 minus PI, okay? Or the likelihood ratio of the two signals depends on the actual state. As long as that is true, there's some genuine information in this structure. In most of the applications, we are going to assume a symmetric matrix, namely we'll set Pg and Pi equal to each other and equal to some value P. Voters cannot communicate. They must vote independently. And as I said, if they could communicate under these assumptions, the problem will be trivial. Now, Shatuki's question was that, this noise in the signal, is it true noise, or is it just the voter's cognitive limitation, that all the information is out there? If you are super smart and super knowledgeable, maybe you can process all that available information to figure out without any doubt what the true state is, but you run into your limitations of knowledge, of time, or attention, and that's why you cannot process all the information. So that's one possible interpretation, right? So one possible interpretation is that the noise is coming from cognitive or knowledge limitations of each voter. Another interpretation is that there's genuine lack of evidence that, the witnesses called to a trial are a subset of the actual people who witnessed the crime, and so on and so forth. It doesn't matter as far as our analysis is concerned. We can think of either interpretation, right? What is important is that to the best of our ability, the voter is not perfectly able to figure out the state for one reason or another. Okay. Now, let me talk about strategies and a few definitions, and then we'll look at it. What are strategies in this simple game? Strategies are mappings from signals to votes. Okay, so each voter only sees a binary signal realization, right? Either a guilty signal or an innocent signal. So after each signal, the voter has to decide how to vote. And we can allow for mixed strategies, and indeed we will allow for mixed strategies in a non-trivial way. So it's possible that after observing some signal, a voter randomizes between voting for conviction and voting for acquittal. We will allow for that. So very generally speaking, this mapping describes a possible voting strategy of each voter. Now, depending on the strategy a voter has chosen, we can give it certain names. A strategy is informative if there's a one-to-one mapping from the signal to the vote, right? For example, if the strategy is to vote for conviction with probability 1 when the signal is guilty, and to vote for acquittal with probability 1 if the signal is innocent, then we have informative voting, right? The voting decision is entirely driven by the signal, right? The signal completely determines how the voter votes. A more general version of that is responsive voting, right? There's a little abuse of notation here, but I think the meaning should be obvious. What is VGVI? This is the probability of voting for conviction, let's say. Yes. So you can allow the voter to randomize as long as the voter has a higher chance of voting or a different chance of voting for conviction when he sees a guilty signal versus when he sees an innocent signal. As long as there's a difference in those two probabilities, we'll call the voting pattern responsive voting, right? So informative voting is a special case of responsive voting where one of these probabilities is 1 and the other is 0. Okay? Now, finally, there's another definition. Let me introduce that. A voting strategy is sincere if the voter votes as if she's the sole decision maker, as if her vote will determine the outcome. Okay, so we can figure out how a voter under this sort of preference and information structure will vote if she was the only one around to make the decision, or if it was a jury of size 1, n equal to 1. Now, In a larger jury, in a different context, if a voter votes exactly that way, we'll call it sincere voting. Right? Sincere voting is where you forget the strategic context, you forget that other voters are involved, they're also basing their votes on some information. You think about your vote as if you are the only one who's calling the shots. That is sincere voting. Yeah.
Sir,
Yes.
could you please repeat the responsive part?
Responsive part is where your probability of voting for a particular decision, let's say conviction, depends on your signal in some way. As long as you have a different probability of voting for conviction when you see a guilty signal versus when you see an innocent signal, we'll call that responsive voting.
Okay, thank you, sir.
Yeah. And so informative voting is a special case of responsive voting where when you see a guilty signal, you vote with probability 1 for conviction. And when you see an innocent signal, you vote with probability 0 for conviction, right? That's responsive to an extreme degree. So that's informative. But if your probabilities are 60% and 50%, then that's also responsive voting. Okay, so I will walk through an example to illustrate what's going on in these sorts of models, and then I'll talk about more general results. So let's take our time to walk through a very simple example, right? It will illustrate a lot of the concepts and issues that we are going to talk about. All right, so we'll consider a very simple setup where there are either 2 voters or 1 voter. Right? So it's a jury of size 2 or a jury of size 1, a judge. And we'll contrast what happens in the 2 cases. The threshold of doubt captured by Q is equal to half. Yes. So whichever state seems more likely, your decision will correspond to that. Let's say the probability on guilt captured by pi has the value 2/3. Right? So everybody starts off believing there's a 2/3 chance this defendant is guilty. And the signal accuracy captured by P is 3/4, right? So 3/4 probability that the signal mirrors the state, and 1/4 probability that the signal is misleading, its value is opposite to what the state is. So what happens when it's a judge, when there's a single decision maker, n equal to 1? Now, the judge will do Bayesian updating after observing his private signal. So you'll have 2 posterior probabilities, probability on guilt after a guilty signal, probability on guilt after an innocent signal, right? And these are the calculations. How do we get it? Standard Bayes rule. See, so let's focus on this. The guilty signal could arise in one of 2 ways, which are mutually exclusive, okay? The first way is that the defendant is actually guilty and the signal is correct, okay? And that probability is pi times p, okay? The other way in which this observation that of a guilty signal could arise is that the defendant is actually innocent, but the signal is faulty. And that probability is 1 minus pi times 1 minus p, okay? So in the denominator, we have the prior probability that a guilty signal will be observed. And in the numerator, we have the prior probability that both the signal and the state are guilty, okay? So that's our standard Bayes rule. And when we plug in the values we have taken, we get 6/7, which is bigger than half. Now, this is no surprise because anyway, the prior on guilt was bigger than half. It was 2/3. And the signal has reinforced that. So it has raised the probability estimation even above further than 2/3. And so obviously that's far away from half, okay? Even without doing the calculations, we could have figured that out. What happens if the signal observed is innocent, right? Where does Bayesian updating lead us to? And here obviously the posterior will come down below 2/3. So the question is whether it comes down enough to fall below half, right? And when we do the calculation, we find that is indeed the case. So our base formula here is this, right? Basically, the innocent signal could arise in one of two ways. First, the defendant is actually guilty, but the signal was wrong. That event has the probability, prior probability, pi times 1 minus p. A second way in which we could end up seeing an innocent signal is that the defendant is actually innocent and our signal is accurate, is accurately reflecting that. So that probability is 1 minus p times 1 minus pi times p, right? Again, you plug in the values, you do the calculation, you get 2/5, which is less than half. So the judge will vote or decide in an informative manner then, right? The signal takes the posterior to the two sides of half. So a guilty signal will be followed by the judge choosing to convict, and an innocent signal will be followed by the judge choosing to acquit. Okay. Now, what is the expected payoff? This is very simple so far. What is the expected payoff? Um, the expected payoff is, remember, Q is half. So that means both kinds of errors, which carry the cost Q and 1 minus Q, both kinds of errors have a cost of minus half, right? Or a cost of half. And the errors will be committed whenever the signal is wrong, because the judge strictly follows the signal. And the signal is wrong 1/4 of the time. So 1/4 of the time, the payoff will be minus half. 3/4 of the time, the signal will be correct and the payoff will be 0 because the correct decision has been made. So this is the expected payoff overall. In terms of errors over here, 25% of the time, the judge will be wrong, right? The payoff is half times or minus half times the error probability here. So error probability 25%. Okay, let's move to a jury of 2. Any questions? Everything clear so far? Okay, so now let's consider a more interesting case. There's jury of 2. Each of them gets this sort of signal with exactly these parameters. There's independent signals. And in a jury of size 2, you can have only one of two voting rules. Either you require unanimity for conviction or unanimity for acquittal. Okay. Let's consider unanimity for conviction. So both of the jurors have to vote for conviction to be the decision. If even one of them vote for acquittal, the joint decision will be acquittal. Those are the rules. Okay. So we have expanded the jury, right? And let's see whether outcomes improve. So now we have two sources of information because we have two jury members. So potentially things can be better, and that's what Condorcet was suggesting to us. Now, what if, okay, so let's say, they both vote according to their signals. Now, what is the overall payoff, or what is the probability of the jury as a whole making a mistake? Okay, that probability is given by this expression. So let's understand it. With probability pi, the actual state is guilty. Okay, if the actual state is guilty, the correct decision is conviction. What is the chance the jury will make a mistake? They will make a mistake if they will avoid a mistake if both of them vote correctly. It's a unanimity rule for conviction, right? So both have to vote correctly for the right decision to be taken. So what's the probability they'll both vote for the right choice? That's the probability that they both get the right signal. Okay, and that probability is p squared. So 1 minus p squared is the probability that when the state is actually guilty, the jury will end up making the wrong choice. Right, so that's one piece. Now, another way in which the jury can go wrong is if the state is actually innocent, that probability is 1 minus pi. And when the defendant is actually innocent, the only way in which a wrong decision will be made, namely the innocent person is convicted, is if both vote incorrectly. Again, under this assumed unanimity rule, right? Both of them have to cast the wrong vote for an innocent person to be sent to prison, right? And that is synonymous with the probability that both of them get the wrong signal. And both of them getting the wrong signal is given by 1 minus p whole squared. So the first piece captures a situation where the defendant is actually guilty and they make the wrong choice. The second captures when the defendant is actually innocent and they make the wrong choice. And you add these two up, the term within the brackets gives you the overall probability of the jury making a mistake. And whenever they make a mistake, of course, the payoff consequence is minus half. So again, you plug in the values, you get this number, right? You double this number, that gives you the error probability. So you can see that the error probability here is more than 30%. Now, if you compare to the judge had an error probability of only 25%. And now we have created a jury of two. We are trying to harness the wisdom of crowds, of the strength of numbers, but things haven't improved. Things have actually deteriorated. So this is bad news for Condorcet, right?
Sir, how is pi the actual probability that he's guilty? That was the prior on G, right?
Yes,
So why are we taking that in to calculate? Like,
it's the prior on G. So we're trying to calculate the overall probability of a mistaken decision. Now, a mistaken decision can be made in both states of the world. One state of the world is where the defendant is guilty, another is where the defendant is innocent. Okay, you have to calculate the error probabilities separately for the two separate states. And that's why pi will come into the calculation. You have to take into account the probability that a mistake is made in the guilty state. The calculation of that probability will obviously involve pi. You also have to separately calculate the probability of making a mistake in the innocent state. And that probability involves 1 minus pi. Right?
yes,
Yeah, we are not, I mean, we are interested in error probabilities, but error probabilities have to be broken up into two parts, right? Punishing the innocent and convicting the guilty. And that's where the pi comes into the calculation. Now, this is a setback for Condorcet and his ideas, right? We have expanded the size of the jury and error probabilities have gone up, not down. Now, if you're a fan of Condorcet, then you should take a look at this and you should be able to come to his defense. You should say that, look, this calculation you did is simplistic. It's misleading. It's not a proper criticism of Condorcet. Why? Well, if it's a jury of two, we have slipped in the assumption that the voters will do sincere voting, meaning they'll pretend like they're still the judge and vote strictly according to their signal, as a judge might have. Yes. Now, is that assumption valid? Is that assumption a good assumption to make? Well, if you believe in Nash and game theory and Nash equilibrium, or Bayesian Nash equilibrium in this case, um, then this is not the right analysis. Okay. The voter will vote strictly according to signal um, only if that's part of a Nash equilibrium, right? In other words, both voters voting sincerely or informatively cannot be a Nash equilibrium in this simple example. If I'm one of the voters and if I think the other guy is voting according to the signals, it can easily be shown that I have a profitable deviation. I will not want to vote according to my signal um, in response. How do we know that? Let's check that. Okay. Suppose the first voter is voting sincerely, right? Votes for conviction whenever his signal is guilty, vote for acquittal whenever his signal is innocent. What should I do? I'm the other voter. Okay. Now, I'll have to calculate two conditional probabilities. I have to update my beliefs. Now, when I update my beliefs, I should condition not only on what my signal is, but also on the event of me being pivotal. Pivotal means that my vote will make a difference, that my vote can alter the decision. That doesn't always happen. Okay. If you're voting in a group of 100 people and the voting rule is simple majority rule, and if 90 of them has voted for one option, then no matter which way you vote, you're not going to be able to change things, right? Let's say there are 101 voters. Okay. Now, if the other 100 voters are split 50-50, then your vote becomes pivotal. Because then whichever way you vote, that will be the collective choice, right? So for some configuration of the votes of others, you will be non-pivotal. For some configuration, it will be pivotal. So when I'm casting my vote, I might as well assume that I am pivotal, that my vote matters. Because if the votes among the other 100 voters is not 50-50, if there's not a tie among them, for those situations, I don't have to worry about it. If the votes are 70-30, then how I cast my vote is inconsequential anyway. It's consequential and it's going to affect my payoffs only in the situation that the other votes split exactly 50-50. There's a tie. And then I'm casting a tie-breaking vote. Coming back to this example, with the jury of 2 and a unanimity rule for conviction, a voter is pivotal only if the other voter has voted to convict. If the other voter has voted to acquit, then nothing matters. Then the decision has already been sealed. It's going to be acquittal. So our second voter, when he's thinking how he should vote, should do his posterior probability calculations based on 2 things, not 1 thing. 2 things. One is his signal. Is his own signal guilty or is it innocent? Secondly, although he doesn't know it, he needs to assume that he's pivotal, that his vote is going to matter. Which is to say, the other guy has voted for conviction. So that's a subtle logic. Is it clear to everyone? Is there a question?
So could you repeat that once?
So let's say, just stepping outside this example, let's go back to the case of 101 voters. So, there's a vote, you're in a class of 101 and you're voting over whether you want to go back to the classroom or whether you want to continue with online classes. Okay, so nobody has given you that power, the authorities, but imagine that is the case, right? So a vote is being taken by but all of you are sitting at home and you can't talk to each other and you're casting your votes independently. And you have some idea of, which may be the correct choice. The voting rule is simple majority rule. So whichever option gets the most votes of the two will be the option chosen. Now, you receive some signal based on your, reading of what's coming out in the papers, what the medical um, opinion seems to be about, the current situation, the health risks, etc. And you're leaning in one way. Maybe you are thinking of voting. Maybe your signal suggests that you should vote for going back to the classroom. Okay. Now, if you're naive as a voter, you will base your vote only on that private signal, based on what you have read about medical experts. But you know that you haven't read everything, that, there's only so much you can read. Many of your classmates have read other stuff, other technical reports, papers, etc. Now, there's a second subtle piece of information which you should take into consideration when calculating your probabilities and your vote, etc., which is that your vote is only going to matter if the rest of the class is exactly split 50 and 50. The rest of the votes has a 50-50 split. Only then will your vote affect the decision. If the rest of your classmates have 70 of them have voted for going back to the classroom and 30 of them have voted against it, which way you vote does not matter. It's inconsequential because the vote is already decided. Okay, so when you are making your probability calculations, you should take into account two different things. One is, what is your private signal? What does your reading say about the wisdom of going back right now or not? Secondly, you should pretend as if the rest of the class is split 50-50, which is to say that you're pivotal. Because in no other situation does your vote matter, so why worry about it? Okay. Now, the reason that's relevant is if others are split 50-50, maybe that means that, the information that others have is very divided. So the fact that others are split 50-50 has information content. Your private signal directly gives you some information, but the fact that you're pivotal and the others are split down the middle also gives you some information. And your Bayesian posterior probability calculations have to incorporate both these pieces of information.
Sir?
Yes.
Sir, so the voter basically anticipates that with some probability he can be a pivotal voter.
Yeah. So I'll come to the issue of, the voter not being pivotal. For the moment, as long as there's some positive probability of being pivotal, a voter's Bayesian calculations, posterior probability calculations, have to condition also on that fact of being pivotal.
But sir, so in this context, the only time that the second person is pivotal is if the first person has chosen to convict.
That's right.
So is it like saying that here, when he's conditioning on being pivotal, it's saying that he assumes that the first guy has chosen to convict?
That's right.
I'm not understanding why we are saying that. I mean, it's like saying that I'm conditioning on the belief that the first guy has already voted in a particular way.
Um, how to put it? Um, I'm trying to think of an analogy which might illuminate it a little bit more. Um, um, So our second voter does not know for sure that the other voter is has convicted. Right? That's not the claim. The claim is the following. Maybe the other guy has voted to convict, or maybe he hasn't. The question I'm facing is, how should I vote? Right? So there are these two possibilities. The other guy has voted to convict, and the other guy has voted to acquit. Now, if you take the second possibility, the other guy has voted to acquit, then this decision problem I'm facing, it doesn't really matter. And whichever way I vote, acquittal will take place anyway. So I don't need to think about this branch of my decision tree, that the other guy has voted to acquit, and I'm worrying about how I should vote, right? For this branch of the two possibilities, it does not matter which way I vote. So this branch is decision irrelevant and payoff irrelevant as far as I'm concerned. Now, the other branch, if the other guy has voted to convict, then how I vote has an effect. It has an effect on the decision, and it has an effect on the payoffs. Okay. So when I'm thinking, although I don't know which of these two possibilities is true, how the other guy has voted, my vote matters only in one of those two situations. So I should basically, as a thought experiment, place myself in that situation where the other guy has voted to convict, and I should ask myself, what kind of vote will improve my payoff in that situation? Right?
Yes, sir, I get it.
So that's why we need to do this conditioning.
Yes.
Yes. In spirit, this pivotal voting logic is very similar to the winner's curse in auction theory, common value auctions. Okay. You guys have studied that a little bit?
No, sir.
So in common value auctions, people are bidding for something like, let's say, the rights to a coal mine or some oil drilling tract, right? They're bidding for something like that. And that's a common value object in the sense that, in a particular area, if there's oil, the value of that, mining rights, drilling rights is the same for everyone, right? Whatever the amount of oil there is, the same amount of oil is there for one company as versus another. And nobody knows for sure how much oil there is, right? They have a noisy private signal about the true common value of the object they're bidding for. Now, people can make their own estimates. They can send out their own engineers and experts, and they make an assessment of how much oil there may be. And your company may have a different estimate from my company. Okay. Now, if the bidders bid according, say it's a second price auction, right? In private values, we know that in a second price auction, it's a dominant strategy to bid your true value. Is that true in a common value auction? The answer is no. Why? Because at the time of bidding, you have some estimate based on your private signal, based on what your experts have told you, right? Let's say they have said, all things considered, there's probably on average around, or in expected terms, around 100 crores worth of oil under the ground here. So should you bid 100 crores? Now, if there are several other bidders, say 20 other bidders, if you bid 100 crores and then at the end of the day, you find that you were the highest bidder, so you have won the rights, that should immediately trigger a winner's curse in you, meaning that your estimate of 100 crores was the highest among 20 different estimates. And the other people are smart and they're trying to, they're basing their estimates on some sort of expertise. So if you come out to be a winner, that means your win was based on not the average estimate of the group, but the highest estimate of the group. In other words, most likely your estimate was an overestimate. So if you had thought before the auction that it was 100 crores worth of value, after winning the auction, your estimate will be immediately revised downwards, maybe to 90 crores, maybe to 80 crores. Yes? And that's why, in order to avoid losses, while submitting your bid, you shouldn't bid your true estimate, you should bid something less than that. You should bid based on two things. You should bid based on one, the signal that you get from your expert, and number two, the event that you're the winner of the auction. Okay? That's a mistake companies often do. They just base their estimates on a signal. They don't also condition on the fact that they've won the auction. Now, they don't know whether they've won the auction or not, but their bid and the price they're paying and the payoff they're making is only relevant if they win the auction, right? If they're not the auction winner, they're anyway, it's a zero, it's a wash. So in auction theory, agents have to condition on winning. They have to, their value assessment should not only depend on their private signal about the common value object, but also on the fact of winning. Similarly, in voting theory, voters have to condition on their private signals, but also on the fact of being pivotal. Right. It's a subtle point. You have to think and digest it a little bit. I hope at least, it's 3/4 clear to everyone. The rest 1/4 will be clear if you mull over it. Okay, but let's apply the logic here in this example. So back to our jury of two. We are going to condition on the signal and pivotality. What does that imply? In particular, let's think of a case where the signal is innocent. So the second voter has got an innocent signal. So if he calculates probability based on, his signal is innocent and he's pivotal, his pivotal means that the other guy has voted to convict. We are taking it as given that the other guy is voting sincerely, right? So the other guy has voted to convict, which means that his signal is G, small g. He got a guilt signal. And my signal is innocent. So these two will cancel out, right, in a symmetric structure. So we are back to the prior. So the posterior in this case is the same as the prior on guilt, which is 2/3. And of course, there's a typo here. The inequality is the other way. So 2/3 is bigger than half. What that means is, if I expect the other voter to vote sincerely, strictly according to his signal, then even if I get an innocent signal, I don't want to vote for acquittal. I still think there's more than a 50% chance that this person is guilty. So I'll cast a conviction vote. So if the other voter votes strictly according to his signal, I don't want to strictly follow my signal. I want to vote for conviction no matter what, even if I get an innocent signal. That's the best response to sincere voting by the other voter. All right. So both voters voting sincerely, strictly according to their signals, is not a Nash equilibrium. And we had based our calculation on that assumption. So the assumption is wrong. So this calculation needs to be thrown out of the window. Any questions at this point? This much clear to everyone? I'm following some logical steps. See how we approach problems like this. Okay, so then how do we proceed? Both voting informatively or sincerely is not a Nash equilibrium. So what is? So the next task then is to identify a Nash equilibrium, isn't it? So can you find a Nash equilibrium of this voting group? A Bayesian Nash equilibrium. How do we find one? Well, let me show you. One Nash equilibrium is very easy. Somebody suggest a Nash equilibrium of this game. It's a simple two-player game, okay? we're trying to find a Bayesian Nash equilibrium, meaning that each voter's strategy depends on his signal. And the two strategies have to be best responses to each other. Can you see a Nash equilibrium in this game? Anyone? Let's start with a simple Nash equilibrium. No? Suppose I think, as one of the voters, that the other guy votes for acquittal no matter what. He always votes for acquittal. When he gets a guilty signal, he votes for acquittal. When he gets an innocent signal, he votes for acquittal. What is my best response?
Non-consequential, what I do.
Doesn't matter. So one of my best responses is to do likewise. Always vote for acquittal. Because how does it matter? Right? So both voting for acquittal, ignoring their private signals, is a Nash equilibrium. It's a mutual best response. So one Nash equilibrium is the defendant always goes scot-free, no matter what signal the two jurors have received. Now, you might say that, this is not a very satisfactory Nash equilibrium. Maybe this is not how they will actually behave. At the very least, we want to know if there are other Nash equilibria. Okay. Now, the situation is symmetric. So you may gravitate towards symmetric Nash equilibria. So is there any other symmetric Nash equilibrium? In particular, is there a symmetric Nash equilibrium which is responsive? This particular equilibrium, both voting for acquittal, is not responsive going by the definition I gave, right? Because the probability of voting for acquittal does not depend on what the signal is. So that's a non-responsive equilibrium. It's a very silly equilibrium where information gets totally shut down. But let's look past this. Can we find a responsive and symmetric Nash equilibrium? Now, both following their signals strictly, that would have been a symmetric equilibrium, but it's not actually an equilibrium, as we just showed, right? So one hope for finding some other equilibrium is to consider mixed strategies, right? So that's what we'll do. Can we find an equilibrium of the following sort? Remember, when we examined deviations, we saw that the tendency is to deviate when the signal is innocent, right? That's when you want to maybe not vote all out for acquittal. So of the two kinds of mixtures, what might happen is after a guilty signal, either voter wants to vote for conviction. After an innocent signal, maybe the voter will randomize, right? With a sigma probability of voting for conviction. Let's see if we can find an equilibrium of this sort, right? Partially mixed strategy. Of course, the question is, what does sigma have to be for this to be an equilibrium? So, as always, to find mixed strategy equilibria, we have to exploit indifference properties. So if this is the strategy, then after an innocent signal, the voter must be indifferent between the two decisions, conviction and acquittal. Yes. And we'll exploit that. Okay. So let's calculate this. Probability of guilt after an innocent signal and assuming I'm pivotal. This is the probability which has to make me indifferent, right? So I'll have to calculate this. Now, I'll calculate it in two steps. First, I'll calculate some interim probability on guilt, given I'm pivotal, ignoring my signal, and then I'll bring my signal in. So let's calculate the first piece. Okay. That's given by this expression. Very quickly, why? Well, I could be pivotal in one of two ways. One way is that the defendant is actually guilty and the other voter has voted for conviction. That's one way in which I can be pivotal. What's the probability of that event? Well, pi is the probability of guilt. Now, the other person either gets the correct signal, G signal, and then votes for conviction with probability 1, or the other person gets the wrong signal, that probability is 1 minus p, And after getting the wrong signal, through randomization, ends up voting for conviction, right? So this is the probability on guilt, and this is the probability that given guilt, the other voter will end up voting for conviction, right? So this is one way in which I could end up being pivotal. Another way in which I could end up being pivotal is that the person is actually innocent, right? And in that case, either the other voter got the wrong signal, namely the guilty signal, in spite of fundamental innocence, or he got the right signal, meaning that he got an innocent signal, but through randomization, he ended up voting for conviction. So this is overall Bayes' rule, right? Just the pieces filled in. And now you insert the values that we have, the parameter values, and you end up with this expression. This involves sigma, and sigma is endogenous, right? But whatever sigma is, this interim probability will depend on sigma in this manner, okay? Let's call this lambda. Okay, so now bringing the second piece of information. I am not only pivotal, but I have observed a private signal, which is I, innocent, okay? So then I'll have to start from this lambda as my prior and do another Bayesian updating, yes? And that is this line, okay? So if I start with a belief of lambda that this person is guilty, I could observe an innocent signal either by mistake, like this, or this person is actually innocent and I saw my innocent signal as a true reflection of that, right? So this is the second round of Bayesian updating, and this gives us an expression after you plug in the value of p of lambda like this. Now, after these two things, I am supposed to be indifferent. If I'm randomizing like this, then after observing an innocent signal and taking into account the fact that I'm pivotal, this probability that I end up with should be such that I'm indifferent between the two decisions. What does that mean? That means this probability should exactly fall at the threshold of doubt, which is Q. So this should equal Q. In our example, Q is half. So I've set this equal to half. The moment I set it equal to half, I can back out the value of lambda that is necessary, which turns out to be 3/4. And the moment I calculate the value of lambda, I can back out the value of sigma that will be necessary, which is 3/7. And that's a legitimate number between 0 and 1. So I have found a symmetric mixed equilibrium where after a guilty signal, they vote for conviction for sure. After an innocent signal, they vote for conviction still with probability 3/7, but vote for acquittal with probability 4/7. This is a kosher, valid, respectable, mixed strategy, symmetric Bayesian Nash equilibrium of this voting data. Okay, now, again, you have to revise these things a little bit to sort of let it sink in. But let me move ahead and calculate the error probabilities under this Nash equilibrium. Okay, what are the error probabilities? Well, we'll calculate it separately for the two states. All right. In state G, for example, you can, maybe I'll talk about one of these two pieces. Let's talk about this. In state I, suppose the defendant is actually innocent. What is the error probability under this equilibrium? Well, one way in which a mistake can be made is both of them get a wrong signal, both get a guilty signal, even though the state is innocent. So both of them cast the wrong vote, namely conviction, and conviction happens. So that's this piece. Another way in which it can happen is that one of them gets the wrong signal and vote for conviction, the other gets the right signal, namely the innocent signal, but through randomization ends up voting for the wrong thing. And that can happen in two ways, right? Which of them got the right signal, which of them got the wrong signal. So that's the two over here. So this is the second way in which the jury as a whole can end up making a mistake. The third way in which they can end up making a mistake is where both got the right signal, the innocent signal, but through randomization, both cast the wrong vote. And that's probability is p squared times sigma squared. So plug in the values of p, plug in the value of sigma that we have calculated, you get 16/49. You can do a similar exercise also for the guilty state. I'm not going to go through it piece by piece. You can look at it and you can see if you follow it. You do the calculation, 13 by 49 is the number that you get. So what is the overall expected payoff? Minus 14.3. Or in other words, what is the error probability? It's basically twice of this, namely 28.6%. So remember, the judge was making a mistake 25% of the time in this example. If you look at a jury of 2, impose unanimity rule, and calculate the symmetric responsive Nash equilibrium, the jury will make a mistake more than 28% of the time. So now you can't defend Condorcet by saying you have looked at non-equilibrium behavior. This is a valid equilibrium. It's not a trivial equilibrium. It's a responsive, symmetric equilibrium. In this equilibrium, the jury has a greater chance of going wrong. Right? So, Condorcet is in tricky waters. It's not that straightforward that, juries will always do better than judges. It depends on many things. And already you can see in this simple voting game, we have already found 2 equilibria, right? So the final defense, if you want to defend Condorcet, is that you can say that maybe, this thing that the jury is doing worse is coming from the fact that we are selecting a particular kind of equilibrium, right? So in other words, is there yet another equilibrium, a third equilibrium? So what do you think? Can you find a third equilibrium? Okay, since I have 2 minutes, yes, there is a third equilibrium, all right? If you looked at a couple of slides back when I was showing that sincere voting by both is not a Nash equilibrium, that gives you the clue to the third equilibrium. Here's the third equilibrium. Voter 2 votes sincerely, sees a guilty signal, votes for a conviction, sees an innocent signal, votes for acquittal. Voter 1 is pig-headed or acts in a pig-headed way and always votes for conviction regardless of the sin. All right. Claim. This is an asymmetric pure strategy Nash equilibrium. Both are playing best responses. Why? Why is voter 2 playing a best response? Well, voter 1 is basically stacking the vote, right? Voter 1 makes voter 2 pivotal all the time. If voter 1's strategy is this, that means voter 2 is effectively a judge. You need 2 conviction votes. Voter 1 mechanically puts in 1 conviction vote. So the ball is always in voter 2's court. And since a judge makes a decision based on his signal entirely, so will voter 2, right? So that part of it is the best response. Now, I already also showed you that if one of the voters is voting sincerely, the other voter always wants to vote for conviction. So therefore, voter 1 is playing a best response to voter 2 and vice versa. So this is a pure strategy, asymmetric pure strategy Nash equilibrium. Now, what is the error probability if they play this equilibrium? This equilibrium essentially mimics or simulates what a judge would have been, right? So if you look at this equilibrium, at least the jury manages to make a tie. The jury does no worse than the judge. Okay? Jury is not doing strictly better, but it's not doing any worse. Okay. Now, you can show that if you can choose the equilibrium, then you can always, if you always select the best equilibrium, then things cannot worsen as you expand the size of the decision-making body, as you're adding more people, expanding the jury. And you can, also investigate Condorcet type results. So things are kind of tricky. There are multiple equilibria in these voting games. Which equilibrium you select affects the answer that you can give. Yes. Now, the next thing I'll do in the next lecture is I'll go ahead and do a more general analysis and cover the paper by Feddersen and Pessendorfer. What they do in their paper is they select this sort of mixed strategy symmetric Nash equilibrium, right? And they look at its properties. So I'm going to talk about that paper the next time. But in this simple example, I tried to show you, and hopefully you have been able to grasp how to work out the equilibria of models like this. Questions?
Sir,
Yes.
sir, initially we had stated the rules of the game by saying that if only there are two like decisions as C, then only the person will be convicted of the crime.
That's right.
So if we change that rule, will the Condorcet like play like will it be like, so we won't give these kinds of contradictions to Condorcet? Will that happen?
Yes. So of course, things are going to depend on rules, right? So I didn't cover or explore all the cases. So what if the rule was not unanimity for conviction in this two-player game, but unanimity for acquittal? Yes. You will get a bunch of different stuff, right? So at this point, it's not exhaustive. I'm trying to show you some techniques, how to, for a given rule, how do we find these equilibria? I've shown you there are multiple equilibria. If you select certain equilibria, things can get worse with a jury. I showed you that possibility. If you select other equilibria, things can weakly improve. If you select the best equilibrium, things will only improve, not go down. So ultimately, the sort of destination ahead is we'll ask the question that, okay, in general, for various kinds of rules, right? Unanimity rules, majority rules, supermajority rules, what can we say about Condorcet's ideas? Yes. So we'll not just pitch the question for majority rule or some simple class of rules, but any sort of rules. And as you will see, whether Condorcet jury theorems come out true or not depend on, to some degree, on the kind of rules that we're talking about. Unanimity rules have, they don't give us Condorcet's asymptotic results. So I'll talk about that the next time. So even with very large juries, you cannot reach asymptotic efficiency if the rules are unanimity rules. So a lot of it is going to depend on rules, but I haven't spelled or mapped all of that out yet.
Yes. Thank you, sir.
Sir?
Yes.
Sir, could you please upload post last lecture's recording on Canvas?
Yes. I'll upload today's and the previous. I forgot. I just realized before class today that I had forgotten to post that. So I'll do it both of these today. Yeah.
Okay. Thank you, sir.
Okay.